a Brownian motion is a martingale. And this is something that you will use a lot in the rest of your studies. So what I want to show is that if I take the expectation of WT plus S given WT, this is equal to WT, okay? Where T and S are two positive quantities, okay? Now, how can I show that? In this way. So I can take the expectation of WT plus S here. I have the conditioning with respect to T, but inside I do the following. I add and remove WT. So I first remove WT and I add immediately back WT. If I do that, you see that I'm essentially adding and removing the same quantity, so I'm always allowed to do that. So if I do this, I can then exploit the properties of the conditional expectation. So I know that if I have the expectation of the sum, this is the sum of the expectations. And this is also true for the conditional expectation. So I can always rewrite the expectation of a sum as the sum of the expectations. So I can do that. I have the expectation of WT plus S minus WT given WT plus the expectation of WT given WT. Okay. Now, let's consider this quantity here first. If I consider the expectation of WT given WT, what does it mean? It means essentially that now I'm at time t, okay? So if I have a random variable, at time t, the process will have a value. So at time t, my process WT has a value that I can observe. I'm not asking what it will be in the future, but I'm asking what it is now when I'm observing the process. Okay, so I'm observing the process itself. And I want to know what is this value? It's like I'm not asking you to tell me what is the value on one share of Apple or one share of Microsoft or one share of Amazon tomorrow or the day after tomorrow. That will be a random quantity. But if I ask you, what is now the value of one share of Amazon? You open the computer, you check, and you tell me, okay, the value is 3. Okay, so if I condition a random variable on itself at the same time instant, essentially this expectation here is nothing more than the value WT itself. What happens for these? For this is a little bit more subtle because you allow me to write this. This is equal to WT plus S minus WT, okay? And I'm conditioning with respect to WT. But I told you that WT can always be seen as an increment between WT and W0 because this is equal to 0. And what do we know about the increments of the Brownian motion? We know that they are independent. So if I know that A is independent from B, if I take the probability of A given B, this is equal just to the probability of A, okay? So it means that also in terms of the expectation, if I take the expectation of something with respect to something with respect to which you are independent, the expectation is just the standard expectation. So it means that this quantity can be rewritten as follows. I have WT, which I copy again from before, and this is the expectation of WT plus S minus WT. And I can remove the conditioning because I know that the increments of a Brownian motion are independent. So if I condition on something on the basis of independence, is like non-conditioning. So there is nothing in common for them. So if I take this, what is this? This is the expectation of an increment of the Brownian motion. So this is the expectation of something that is normally distributed with mean 0 and variance equal to the length of the interval. So what I know about this quantity is that this quantity here is normally distributed with mean 0 and variance equal to t plus s minus t. So this is deleting. So this is a normally distributed random variable with mean 0 and variance s. So what is the expectation of this random variable? This expectation is just 0, so it deletes. So what you see is that we have proven exactly this fact.